Today I am actually going to use my microphone because the complexity of this task, implementing load store operations, is too great to really use annotations to do justice for. So this is part of the logic of the control circuit for the CPU. Over here I have the data bus split into two lines, data in, data out, and the address control line hanging overhead. This selects the memory address for reading and writing to. Over here we have the control logic. It's made up of several portions, so this bottom part here is a clock which I could use when I actually have it running. The server is under a little bit too much load when that's running for me to be able to reliably stop it. So at the moment it pipes into this unit here, which is a once only toggle. So the cool thing about this is I can hit it once, it will toggle once, and then it waits for me to turn it off before I can turn it on again. Due to the von Neumann-like structure of this processor, it has a mix of 1 and 2 cycle instructions. Load and store are 2 cycle instructions, so there's a little bit of logic in here just to check whether it's a load or store instruction, and if so, keeps memory here, remembering whether it's a 1 or 2 cycle instruction. This is just a 1-bit register, and there's another 1-bit register that, using the free version of Fraps. So this is a 1-bit register that keeps track of what cycle it is on a 2 cycle instruction. On the display here I can display the control sequence. Now the way this CPU control unit is designed is it runs on modules, and it is assumed that each module has access to all the control and data paths it needs to perform its task. So the task of this module is to tell each control module whether it is supposed to be active for the cycle or not. This particular module also controls a normal program counter increment. Jumps will be handled by another module which I haven't made yet, and during the 2 cycle increment, 2 cycles of load and store operations, there is no increment. Well, except for the 2nd cycle obviously, but the 1st cycle has no increment. Now over here we have the logic for the load. This has one 8-bit register and a 3-bit register internally. The 8-bit holds the address that's going to be loaded from, and the 3-bit holds the register that's going to be loaded to. So on the 1st cycle what it does is it loads those values from a register in the system, loads the address, and then it loads the register, and on the 2nd cycle it makes those happen. It also includes a special function which is I've called load previous, which allows, because I'm using an 8-bit instruction set, there is no load immediate value, so instead I am giving you the option, if you want to save a value to register 0, register 0 is an invalid address to write to, it's always 0, but if you give it that instruction it will take that as a load previous and actually load the previous instruction as a data value. This can be utilized in using a jump instruction to have 8-bit immediates within the code that you are writing. Over here we have a store logic block, runs similar to the load except nothing special here. It's got an 8-bit register to keep track of the address to be written to from the 1st cycle, and a 3-bit register to keep track of the register that is going to be read from in the 2nd cycle. I also modified my register table so that you can see the data on this row of blue lights. are currently inactive because there's no data. Now all the registers in this processor reset when the power is turned off, and this is the power switch over here. So I'll just turn that on, and this block here links up to my toggle, so I'm going to toggle through running some instructions, but before I do that I'll actually show you those instructions. Yep, they're all the way at the end of the RAM block at address 0, which is where the computer starts from. So in address 0 we have read from register 0 and address and write it into register 2. Register 0 of course being the value 0, that means this instruction actually writes itself into register 2, and it's the address value 40. Sorry, least significant bit is left in the RAM. Then we have this next instruction, which is read from the address specified in register 2 and load it in register 3. Now the address in register 2 is 40, so we'll go have a quick look and see what's in 40, which is in the second arm of RAM, if you like, here, and it's the value 7. Going back to our instructions, the next instruction in position 2 is actually just FF. It's not an instruction. Well, it would be an instruction, but I haven't implemented it yet, so at the moment it's a data value that is just being skipped by virtue of not being processed. Instruction 3, then that's a load instruction, and that's a load previous. You see it's trying to load into address 0. So what this does is it loads into register 4. Now interestingly, the registers in the instructions are least significant bit right, despite the fact the data is stored the other way, so that's perhaps a minor inconsistency there. But that value there, FF, into register 4. Now the following instruction is quite cool. This is a store instruction, and it stores into the address specified in register 3, which we know from looking at the data is address 7, the data held in register 4, which we know from the previous instruction is FF. Now address 7 is at the bottom of this block here. So when this instruction finishes writing, this block here should contain the value FF. And the final instruction here is a jump to nowhere because I haven't implemented it, but it's just enough to keep the processor just sitting forever in a loop at that line because the program counter is not incrementing yet for jumps. So we can see this running now. Power is already on, but I'll just toggle it. Just to ensure that the registers are empty. And now I'll swing round and you can see parts of the processor running. If I get out a decent enough distance, we might be able to see some of the data being held in the registers while they're being calculated. Now at the moment the CPU doesn't do any calculations on data yet. It can. The ALU has been completed by divide and multiply instructions, which I may actually remove and replace with a rotate instruction and change the machine code for the get instruction, which currently is piggybacking off a spare bit in the jump instruction. When I upload the fully working version, I will also post the assembly code that I've designed this to run on. Just in case people were wondering, this is all me. I haven't used any textbooks. I've studied computer science, particularly advanced CPU design, and so this is just straight out of my head. So anyway, power's on, so we can start toggling through instructions. So that's a 2-cycle instruction, and it's loaded the first line into register 2. Second instruction, so this is the first cycle of the second instruction, which sets up the conditions. And then the second cycle, which applies it. And as you can see, we now have the value 7 sitting in register 3. Now we're just going to load up the instruction FF. That does nothing, so it won't change anything. It will just increment the counter and move on. Instruction 4, actually it's address 3, sets up the value and reads the previous instruction into address 4, as we can see there. And now I think we're at the store command. Love the break in my voice as I question it. I'm 33, that's a bit embarrassing. Set up, and the second command should actually execute it, and we should see it all light up just like that. And as I said, the final instruction is just 01, which is not implemented yet, so this will just sit there doing nothing with the program counter not incrementing. Right, and now we can go and look at what the program did. So in address 7 we should see the value FF, and voila, there we have it. Load and store instructions working complete. I don't think there's any hardware bugs sitting in this, but I've fixed a few as I've gone through after I've made videos. I've encountered things mainly caused by having activation blocks where I should have used ORs or ANDs. Yeah, so the next video in the series should be Hello World, which I will post the assembler for. I will post the instruction set, and of course that will be accompanied by a video of it operating. It will be slightly slower because I'm not going to hard code it. I'm going to use a Pascal style string so that I can show the ALU working as well, and the direct memory addressing of the display. Catch you later, and thanks for watching.